I'll be divided by 4, divided by 1.
So since n, right, is the number of times compounded per year, we're going to divide by 4. And then take that and raise it to the n, number of times compounded. So again, 4 times the number of years, 5. We're going to do 5 years here. Okay, so again, this is a compound a certain number of times per year. We'll just fill in all of our variables there. Okay. And then we just put this into our calculator. You can, if you are like good with your calculator typing skills and stuff like that, you can do it all at once. Okay, so I mean, 12,000, parenthesis, 1 plus 0.083 over 4 to the 20th. So you get like $18,095.43. So that's if we compound it, starting with $12,000 over 5 years at an interest rate of 8.3%. You'll end up with $18,000.95. $99.43. Okay. So let's compare that now to continuous growth. Okay. So again, same principle, 12,000. Okay, it's the number e to the 0.083, okay, times t, which is again 5. So we'll type that into our calculator. 12,000 e to the 0.083 times 5. And we have a slightly different number, a slightly higher number, 18,172.45. So all other things held the same, right? All other things kept the same, all other things being equal, just deciding between quarterly or continuously compounding, right? Obviously the continuously here is a little bit better, right? You get not quite $100 more, right? Just under $100 more, but not just under, but under $80 actually. But anyway, the idea being that you do get more money here for the same amount of work, we'll say, you know, so continuously would be more attractive there in that case, right? So we want that continuous growth. Okay, slightly different. All right. So number 2 then, slightly different kind of question. Find the number of years required for a $3,000 investment to double when it's at a 7% interest rate compounded monthly versus compounded continuously. Okay. So here in this case, we're asked to find the number of years, which means we'll be solving for what variable? T, right? Yeah, time. Okay, we don't know what T is. Okay. This $3,000, what is that representing then in this case? The principal, the initial amount, right? That's our P, okay? And we want our investment to double at, okay, 7% interest rate. So there's our R. R is 0.07. And then compounded monthly, that means we're going to go to our compounded n times per year. And if we're compounding it monthly, that means how many times will it be compounded in a year? 12, right? So n equals 12. Okay, so let's take our A equals P times 1 plus R over n to the nt. Okay, and we'll say here that, okay, our principal is 3,000, our rate is 0.07, n is 12, and then 12 times t. We run into a bit of a problem here. We plug everything in because we have 2 variables, a and t. We want to solve for t, but we also have this a in here. What's a for that, Sophie? Right. We know what our final amount is. We're not told what the final amount's going to be, but we know we want our end goal to be double the $3,000, right? Okay? So we'll put 6,000 in here. That would be double the initial amount. And then we can solve from there. So we can, divide both sides by 3,000. We get 2 there equals 1 plus 0.07 over 12 to the 12t. And then, of course, our variable here, the thing that we're solving for, that t, it's in the exponent. We want to get that t out of the exponent. So what can we do here to both sides? Yeah? James?
Log base 1 plus quantity 0.07 over 12.
If you want to do it that way, absolutely. I'm going to use just natural log here, but that's fine. You can use log base, whatever you want there. I'm going to use natural log. And so we're going to have with natural log of 2 equals, and then 12t times the natural log of 1 plus 0.027 over 12. That's a matter of personal preference. James chose to use the base for his log base. So he did log base this number, 1 plus 0.07 over 12. Okay, and that's fine. You can do it that way. It's going to be slightly different in the solution, but the final answer will be the same. I chose to use natural log because I'm lazy and I didn't want to have to write like a little small base, of that. So we're just going to leave it like this. So anyway, so solving for t here, right? We have t times the 12, but also t times the natural log. So I'm just going to divide both of these things over. We have natural log of 2 over 12 times the natural log of 1 plus 0.07 all over 12. Like that. So there's our answer. That's our exact or our precise answer. But of course, let's actually solve it out here and see what we get. So, and again, you can type this whole thing in if you're good. Okay. And so I get approximately 9.931. And again, this is something where, part of the trickiness of this problem is being able to type this into your calculator correctly and getting the 9.931. Okay, so I recommend, if you guys, I suggest you try and type it into your calculator. Make sure that you can, in fact, get the 9.931. So you're not set yourself up for trouble later on down the line when you think you know how to do it, but you actually have some problems with it. Excuse me. Okay. If we go back and check it by plugging the 9.931 in for the t, which I did here, you'll notice we don't get exactly 6,000, right? But that's because we rounded our t value, right? So we rounded t. Yeah.
You don't have to use the change-based formula, right?
You don't. There is no way to do logarithms without the.
You can put a log base something.
Oh, is that right? What's the command?
Math. No.
Oh, log base a. Is that what it is? Maybe I don't know. Would that work? Yeah.
That's not right there.
It's this one right here. Oh yeah, that's nice. It's pretty neat. So there you go, guys. Alright, you can do whatever you want. Mine even has pretty type. I don't know if you guys, let me turn off pretty type here and see what it looks like. It's probably yucky. Let's see here. Math, num, nope, math, log base. Yeah, so that's kind of funky. I'm guessing log base 2 of 4, 2 to, ooh. It's the reverse, yeah. So this is what you're evaluating, and then that's your base, which that's kind of annoying. Okay, so it's like if you have a calculator that doesn't have pretty type, this is what you have to use. So this logarithm I just typed in. When I typed in log base 2, 4 like that, that's really evaluating log base 4 of 2. Yeah. Okay, so be careful. The last number is the base, and the first number is like the number that you're evaluating. So just be careful with that. But that's good. Okay. Or again, if you prefer, you can use change of base. Either way. Okay. So continuously. All right. Moving back here, number 2. So there's 9.931. That's how much time it would take in years to take your $3,000 investment and to have it double, given a 7% interest rate. Okay. So now let's take a look at what happens when we use compounding continuously. Okay. Earlier, right, when we did compounding quarterly versus compounding continuously, we got more money in the same amount of time and the same interest rate. So we expect here that the amount of time required to double should be what? Less. Yeah, smaller. So let's see here. So we'll put that 6,000 in here. 0.07 t. So you get 2 equals 0.07 t. And then here, natural log really does lend itself to this because we have an e, so we could just really just say natural log of 2 equals, 0.07 t, right? And then divide that 0.07 over. And let's see here. 9.902. So, oops, squiggly equals, there we go. Okay. So in comparing these two, right, in fact, compounding continuously, it's a lower amount of time. It's a smaller amount of time to double your money. Not that much smaller, but smaller still. Okay. Questions on any of that? So, there we go. Power of compound growth.